everyone, and welcome to class. I am absolutely thrilled you're here today because we are going to unlock some actual, real-life magic. Well, okay, scratch that. It's not magic, it's physics. Today's explainer is a step-by-step lesson exploring those invisible forces that surround us every single day. I've got my science teacher hat firmly on, and together we're going to break down the incredible world of magnets. So grab your mental notebooks, get comfortable, and get ready to have your mind blown by some everyday science. Here's the roadmap for today's lesson. We'll be building our understanding from the ground up, starting with magnets in everyday life, then magnetic versus non-magnetic, visualizing magnetic poles, compasses, and Earth's magnetism, and finally wrapping up with the laws of attraction. All right, kicking things off with Section 1, Magnets in Everyday Life. You know, we often think of physics as something that only happens in these high-tech, super sterile laboratories. But the truth is, you've been carrying a literal physics experiment around with you for years. Have you ever wondered how your pencil box mysteriously snaps shut, seemingly pulled by an invisible hand? Or how a purse clicks perfectly closed all on its own? That super satisfying snap happens right inside your backpack. It's an invisible force field at work, doing the heavy lifting to keep your pens from spilling absolutely everywhere. Okay, let's dive into this. Think about incredibly common household items. Pencil boxes, those little latches, and of course, your classic fridge magnets. These are all what we call artificial magnets. Because magnets are just so incredibly useful, we've learned to manufacture them from materials like iron, shaping them into all sorts of convenient forms. You're probably familiar with the classic long bar magnet, the U-shaped magnet, and the circular ring magnet. But here's the thing, way before we had factories pumping out U-shaped magnets for our refrigerators, nature actually had its own version. Thousands of years ago, people discovered this naturally occurring magnetic rock called loadstone. I mean, imagine being an ancient sailor out on the treacherous seas, right? A massive storm rolls in, the sky becomes totally overcast, hiding the stars you rely on to navigate. In that moment, loadstone was literally a lifesaver. This magical little rock naturally pointed them in the right direction when all their other guides completely disappeared. Moving right along to Section 2, magnetic versus non-magnetic. So let's do our very first mental live lab demonstration. We know magnets have this invisible pull, but what exactly are they pulling on? Does a magnet stick to a piece of wood? A plastic cup? If you think about Activity 4.1 in a standard textbook, it's essentially taking a magnet and walking around testing it on different objects. And you'd quickly realize that magnets are incredibly picky. They completely ignore most materials, things like plastic, wood, and glass, totally non-magnetic. But they fiercely attract certain metals. The big three VIPs of the magnetic world are iron, nickel, and cobalt. If an object contains these specific metals, that invisible force is going to grab hold of it. We call these magnetic materials. All right, Section 3, visualizing magnetic poles. Now that we know what a magnet is actually attracted to, let's try to draw a map of the unseen. If you were to sprinkle tiny, tiny pieces of iron, called iron filings, onto a piece of paper and place a bar magnet underneath, the filings don't just sit there randomly. They are instantly pulled into a highly specific, very distinct pattern. It's like they're literally drawing out the invisible magnetic field lines for us to see with our own eyes. Now really take a close look at that pattern. Notice how the iron filings aren't distributed uniformly across the bar? The vast majority of those tiny iron shards are fiercely clustered right at the very ends of the magnet. Barely any stick to the center. And this proves a vital physics concept. A magnet's invisible force is not uniform. Its strength is heavily, heavily concentrated at the extremities. We call these high-powered ends the poles of the magnet. And here is where physics gets absolutely mind-blowing. These poles are called the North Pole and the South Pole. Now, you might be thinking, well, hey, if the North Pole is on the left and the South Pole is on the right, I'll just snap the magnet in half to get one of each. Nope. No way. It is entirely impossible to isolate a single pole. If you smash a magnet into smaller pieces, new North and South poles instantly form on those newly created pieces. They always, and I mean always, exist in pairs. Okay, Section 4, compasses and Earth's magnetism. All right, class, it's time to scale things up. We've looked at tiny iron filings on a piece of paper, but now we're going to expand our laboratory to the magnitude of planet Earth itself. Remember how those ancient sailors utilized lodestone? Well, they were capitalizing on a fundamental behavior of these poles. When a magnet is allowed to pivot freely, without any friction holding it back, its poles become what we call seeking poles. One end will stubbornly insist on orienting toward geographic north, and its counterpart will point toward geographic south. Let's see how this builds our understanding with another classic experiment, activity 4.3. Imagine you take a thread, tie it perfectly to the midpoint of a bar magnet, and just let it hang there, suspended in the air. Give it a gentle spin. When it finally stops rotating, it will come to rest precisely along a north-south axis, every single time. Why? Because the Earth itself acts like a gigantic magnet. Your miniature bar magnet is literally aligning its invisible force field with the massive invisible force field generated by our own planet. This incredible property is exactly how the modern compass was engineered. A compass is essentially just a tiny, extremely light magnet shaped like a needle. It's perfectly balanced on a pin inside a circular box so it can rotate completely freely. And to make it super easy for travelers and explorers to read on the go, the end of the needle that points north, the north-seeking pole, is usually painted red. Now, what's genuinely fascinating here is the sheer penetrating power of that magnetic field. Think about the setup from activity 4.7. We have a compass needle responding to a bar magnet, but there is a solid block of wood positioned right between them. And guess what? The compass needle still deflects, it still moves. The magnetic effect slices straight through non-magnetic materials like wood, glass, and plastic without even slowing down. It's wild. Which brings us to section 5, the laws of attraction. As we head into the final stretch of our lesson, we really need to examine the dynamic interactions that happen when two independent magnetic fields crash into one another. To really visualize this, we use a setup that looks kind of like a thrilling miniature race. This is activity 4.5. By resting bar magnets on top of a row of round pencils, we completely remove the friction of the table. They're essentially on little roller skates. When we bring a second magnet close by, we don't just feel the pull in our hands. We can literally watch the magnet on the pencils accelerate toward the approaching magnet or violently roll away from it. This interaction follows an absolute, unbreakable golden rule of the universe. When you bring two magnets together, unlike poles attract each other. That means a north pole and a south pole will pull together in a tight embrace. But like poles repel each other. A north pole will aggressively push away another north pole, and a south will push away a south. So the absolutely crucial point here is this. How do you know for sure if a piece of metal is actually a magnet or just a random piece of iron? Think about it for a second. Normal iron is attracted to both the north and south poles of a magnet. It just wants to stick to everything. But a true magnet will only attract to opposite poles, and it will actively repel a like pole. Therefore, in physics, we say that repulsion is the only sure test to identify a true magnet. If it pushes away, you've got a magnet for sure. And finally, section 6, lab safety and conclusion. Excellent job today, class. We've covered some immense ground. But before we finish up and pack our equipment away, we need to have a quick, serious discussion about lab safety. Magnets can actually lose their properties if they aren't stored correctly. You should always store bar magnets in pairs, laying them side by side, but with their unlike poles adjacent to each other, so north next to south. You keep them separated by a piece of wood, and then you place two pieces of soft iron, called keepers, right across the ends. This essentially bridges the magnetic circuit and keeps their potential energy perfectly intact. You also really have to treat them with respect. Simply put, if you abuse a magnet, it will die. Heating them over a flame, dropping them on a hard floor, or hitting them with a hammer scrambles their internal alignment and totally destroys their magnetism. And of course, because these invisible force fields easily pass right through plastic cases, keep them far away from mobile phones, televisions, and computers, or you might cause some serious, expensive electronic damage. Before we wrap up, I'm going to leave you with one final, totally mind-bending thought to chew on until our next explainer. We learned today that if you break a magnet in half, you don't separate the poles. You just create two smaller magnets, each with its own north and south. So, if you took a tiny laser and kept cutting that magnet smaller and smaller and smaller, exactly how microscopic can you get before those poles finally disappear? Do they ever disappear? Think about that incredible journey all the way down to the atomic scale. Thank you so much for joining me in class today. Keep questioning those invisible forces around you, and I will see you next time.